In this lesson, we're going to examine compound events. So we've looked at mutually exclusive events, things that can or cannot happen at the same time. Here, compound events, we're going to look at situations where we have sequential events. In other words, something happens after the other. Not necessarily at the same time, but one, then the next, and the next, and the next. I roll a dice, and then roll it again. Or I roll a dice, and then I flip a coin. Okay? To deal with these things, we have to decide if they're independent or dependent. Independent events means that one event has no effect on the next. So if I flip a coin and then I roll a dice, those two things have nothing to do with each other. Okay? Really easy to just calculate that because all I have to do is multiply one by the other. Okay? And the word we're looking for here is going to be the word and. I roll a dice and I flip a coin. Okay? To do these things, the easiest way, we can't use Venn diagrams because we don't have overlapping things, but we can make tree diagrams. A tree diagram helps show the stages of the problem and the probability at each stage. So a tree diagram is going to have branches, and we have more branches off of those things. And what we're going to need to do is figure out the probability of each stage. So probability here, and then we're going to multiply the probability here, and then multiply the probability here. Every time we add a branch, we add a stage, we add multiplying. Okay, so we're going to try one, a nice simple one to start. So a game consists of rolling a die and then cutting a deck of cards. Find the probability that a 6 is rolled and a 6 is cut from the deck of cards. Let's move this down for just a second here. So I want to get a 6 and a 6. These two things have nothing to do with each other. Rolling a dice, cutting a card have absolutely nothing to do with each other. So I can simply find the two things separately and multiply them together. What's that going to look like? Well, if I roll a 6, what's the probability of doing that? That's 1 out of 6. Times, what's the probability of getting a 6 from a deck of cards? Well, there's 4 of them out of 52. Remind with fractions, you're multiplying. You can use your fraction board in your calculator or just go straight across. That's probably faster. 1 times 4 is 4. 6 times 52 is 312. Okay, now, that's the formula way, but I said there's also a tree diagram way. So let's take a look at the tree diagram. A tree diagram is what could happen at each stage. So stage 1 is either I get a 6, and we're talking about rolling a dice, or not. Stage 2 is getting a 6 again, but with the cards. So I could get a 6 or not. I could get a 6 or not. And that's my tree diagram, the situations that could happen. And notice that the second set of branches, this set right here, is the same for the top half as it is for the bottom half. Because it doesn't matter what happened first, it's an independent event what happens next. So this time, when we have the tree diagram, we have to add the probabilities to it. So let's get rid of that. What's the probability of getting a 6 with the dice? 1 out of 6, which means not would be 5 out of 6. Together, those two things should add up to 100%, or in other words, 6 out of 6. With the cards, there's 4 out of 52, and that would mean this is 48 out of 52. 4 out of 52, 48 out of 52. And these probabilities are the same because it's an independent event. And then to do the math, we would, like we did with the formula, multiply the two things together that we want. Get a 6 and then get a 6. So in this situation, the tree diagram actually seems a little more complicated, right? But at times, when there's lots of things going on here, the tree diagram will actually help you organize your math a little better and make it a little bit easier to figure out. Let's try the next one. What is the probability of tossing 5 ones in a row with a single die? Again, we need to ask ourselves, independent or dependent? Just tossing a dice and getting one the first time mean it's going to happen again the next time and the next time and the next time? No. Pretty unlikely this to happen, but they don't affect each other. So the probability of getting 5 ones in a row would mean a 1 the first time, and a 1 the next time, and a 1 the next time, and a 1 the next time. We're going to do this 5 times. Each of these things are independent of one another. What's the probability of getting 1 1? That's a 6. and a 6, and a 6, and a 6, and a 6. And if I multiply it all together, 1 times 1 times 1 times 1 is 1, and 6 times 6 times 6 times 6 times 6 is 7,776. Not very likely. Okay. I think it makes more sense using a formula for that one. Tree diagram is just a messy thing. But let's try this next one with a tree diagram. Okay. So we have Justin. Justin estimates that the probability of passing mathematics is 0.8. Passing English is 0.9. Assuming these events are independent, and we have to assume that. They don't tell us that, oh, Justin's not very good at school, or he doesn't try, or things like that. We don't know enough about the situation. We can assume they're independent. Find the probability that Justin will, and we have some situations. So here's a situation where I don't have just the basic numbers. I might want to think about what's going on here. So I'm going to make a tree diagram. So stage 1 is he can either pass math, or not, fails. And depending if he passes math, he might pass English or not. And he could fail English and still pass fail math and still pass English, or not. Okay. I'm going to put some values in here that I know from the question. The probability of him passing math, it tells us, is 0.8. So it means failing it will be the opposite, the complement, 0.2. English is 0.9, so failing is 0.1. English is 0.9, so failing is 0.1. Okay, let's try the questions. Pass math and English. So math and English. All these things are independent, so I can very quickly multiply the two things together. In other words, I can follow the branch of my tree diagram, these ones right here, and I'll get my answer. 0.8 times 0.9 is 0.72. Okay, we'll pass math, but fail English. I'm going to put that one down here, okay? Math, but fail English. In other words, not get English. Again, I can follow the branch of my tree diagram. So I want to pass math, but then not pass English. So I'm going to multiply 0.8 times 0.1, another 0.08. And then the last one will pass at least one of his classes. So let's talk about this last one for a second here. Passing at least one of his classes means we have more than one situation. Okay. He could, let's think about this here. He could do pass math and English, pass both, or he could pass math and not get English, or he could not pass math and get English. There's 3 different situations. So when I come across this idea of or, and if you think about it for a second, these are mutually exclusive. They're independent of one another. They don't have any effect on each other. So I've got to figure them all out separately. Math and English. Well, I've actually figured that one out already. That was part A. The answer was 0.72. Okay. Math but not English was actually part B. This was 0.08. Part C is a new set of branches. Part C is not math, but yes for English. Okay, so that's new for us. This is going to be 0.2 times 0.9, which is 0.18. So to pass at least one class, I'm going to see that, at least one. I'm going to have to add 0.72 plus, because it's a different situation, or plus 0.18. And I'll get my answer as 0.98. There's a 98% chance he'll pass at least one. But there's one more little idea I want to talk about with this question that maybe, hopefully, your brain hooks onto. Could we figure out the probability of failing both? Is that not the last branch of our tree diagram, the 0.2 and the 0.1? In other words, there's 2%. Well, passing at least one of his classes means that he didn't fail both. In other words, It's the complement. So if you think I want to pass at least 1, means I should be able to take the total, which is 100%, or in other words 1, and get rid of what I don't want, failing both, and I'll be left with what I do want. And this is a kind of a big idea. It's a shortcut for doing things that have multiple cases. If I get rid of what I don't want, in other words, the complement, I'm left with what I do want. Okay, so there's 2 different ways of approaching that question. Hopefully you pick one that makes more sense to you. Okay, so we've been talking about independent events, things that don't affect each other. Well, what about dependent events? If things are dependent on one another, that means the results of one thing directly affects the next thing. Okay, so for instance, the probability of doing 2 aces in a row. So our formula kind of looks the same. A and B is the probability of A times, and here's our new thing. This means B given A has happened. Okay, or B that has occurred. So if I think about the idea of dealing 2 aces, the probability of an ace and an ace. Well, the first time I deal an ace, there's 4 out of 52. But the next time, we're multiplying here still, the next time, there's not 52 cards in the deck anymore. Nor are there 4 aces anymore, because there's one on the table in front of you. So my probability changes. I'm down to 3 aces of the remaining 51 cards. Because my probability has changed at each stage of the problem, we call this dependent. Okay, it's like pulling the names out of a hat. Once you pull out one name out of the hat, there's less names in there, people's likelihood of winning something go up. Right? The more and more and more you pull, you're down to the last name, there's a 100% chance you're going to win because there's only one left in there. Okay? But the process kind of stays the same. We can make tree diagrams, we can put probabilities on them, we can multiply things together. So let's take a look at this example. The probability that it will snow tomorrow, 0.3. If it snows tomorrow, the probability that Chuck's going to be late for school is 0.8. If it doesn't, he's going to be late as 0.1. So let's do the tree diagram for this. What has to happen first? It either snows or not. If it snows, Chuck is late or not. If it doesn't snow, he's still late or not. Just those probabilities change, that's all, right? So probability of snow is 30% or 0.3. So not snow would be the opposite, the complement. If it snows, late is 0.8. So not late is 0.2. However, if it doesn't snow, late's down to 0.1. So notice this time in my tree diagram, the second set of branches, the probabilities are different because it depended on what happened first. Let's try some questions here. Find the probability that it does not snow, so not snow, and late. So in my tree diagram, I need to do not snow, that's 0.7, and late. Late is 0.1 on that branch. So there's a 7% chance of that happening. And if we try part C, find the probability that Chuck is late. Well, by just saying the word late and not telling us about snow, we don't know what the situation is. Is it snow and late, or is it not snow and late? Well, I can figure out those 2 cases separately and add them together. I've already figured out the second one. That's part A, 0.07. I can figure out the first case by going back to my tree diagram. Snow and late. Snow is 0.3, late is 0.8. So 0.3 times 0.8 will give us 0.24 plus 0.07, or in other words, there's a 31% chance he's going to be late tomorrow. Okay, last one. Give it a try, pause it, see what you can do. Local grocery store is offering free samples. The experimental probability of a shopper accepting a sample is 15%. The conditional probability, so in other words, if something has happened, that the customer purchases some juice given that they accepted the sample as 20%. No one purchases juice without sampling. Okay, if they offer 500 samples, how many sales did they make? So I want to know what's the probability that somebody bought something, right? So in order to buy something, they had to sample it. And I know that because it said no one purchases juice without sampling. So I need to figure the probability of sampling and purchasing. Now, maybe this is confusing, so we look at a tree diagram. What's the probability of sampling or not? What's the probability of purchasing or not? Purchasing or not. Okay, what's the probability of sampling? Oh, it's an experimental probability, 15%, so 0.15, which makes this 0.85. Probability of purchase, if they had a sample, was 20%, 0.2, 0.8. If they didn't sample, it says no one purchases juice. This is 0, and this is 100%. Okay, if they offer 500 samples, how many sales do they make? So we need sampling and purchasing, which is that part of the tree diagram. 0.15 times 0.2 gives us 0.03. Only 3% of people actually did this. The question wasn't what the probability, though. It says how many sales do they make. So our sales, there's 500 samples. 3% of those people accepted it. Oops, 0.3. So we end up with 15 sales. Okay, not very much. And that's our big idea for today. So compound events. I think tree diagrams are really handy. Put the right numbers in the right spots and just follow through. Be careful sometimes if you have cases to look at. You may have to add up different things like we did in the previous example. Some questions you can try. If you're stuck on them, come see me. We'll figure some things out together.